Starting with the initial trigonometric functions or trig functions, we have here a right triangle. We'll later label this a 3, 4, 5 right triangle, but for now, if we're talking about this angle over here, we'll just call it theta, then this side over here is the adjacent side. The side opposite is the opposite side, and the longest side is the hypotenuse. So when we're talking about the trig functions, those functions are sine, cosine, and tangent. And a common word, when I went to school, they said that there was this Indian word, and it was SOHCAHTOA. So this is an acronym, and for sine, it means opposite over hypotenuse. For cosine, it means adjacent over hypotenuse. And for tangent, it means opposite over adjacent. Cosecant, secant, and cotangent, which are simply the reciprocals of sine, cosine, and tangent. So cosecant is hypotenuse over opposite, secant, and that is hypotenuse over adjacent. And finally, cotangent is adjacent over opposite. Let's label the triangle a 3, 4, 5 right triangle and use the 3, 4, and 5 to find the sine, cosine, and tangent for this triangle. So for sine, we have opposite over hypotenuse, which is 3 over 5. Cosine is adjacent over hypotenuse, which is 4 over 5. And finally, tangent is opposite over adjacent, which is 3 over 4. Looking at the first of the identities, we'll use the quotient identities. So the first one is that tangent theta is equal to sine theta over cosine theta. And since I'm not a fan of memorizing things, let's take a look at where it actually comes from. If we look at the quotient of sine, which is opposite over hypotenuse, over cosine, which is adjacent over hypotenuse, well, when we divide one fraction by another fraction, we actually do a copy dot flip. So here we have the two fractions. In order to change it into multiplication, I replace the division symbol with a dot, and I flip the second fraction, so copy dot flip. So what we have is opposite over hypotenuse times hypotenuse over adjacent. The hypotenuse divide through by 1, and when I multiply straight across, I get opposite over adjacent. And as we can see over here, opposite over adjacent is tangent. Well, the same holds true for cotangent. So since cotangent theta is going to be the reciprocal, it's cosine theta divided by sine theta, written out. So we have cosine theta is adjacent over hypotenuse divided by sine theta, which is opposite over hypotenuse. Doing copy dot flip, we see that we have hypotenuse goes into itself once and again into itself once. So then we have adjacent over opposite. Our next category covered will be the Pythagorean identities. So here we have the Pythagorean theorem, and it mirrors what the Pythagorean identity starts out as, which is sine squared theta plus cosine squared theta equals 1. And now we can manipulate this to come up with the Pythagorean identity, so it's not really an issue of memorizing, but rather understanding how to derive them. So to start with, if I divide all three terms by sine squared theta, well, the first term is going to be simply 1 plus. Now, cosine squared theta over sine squared theta, if you recall from before, that was cotangent. So this is cotangent squared theta. And what over sine squared is the reciprocal of sine squared theta, which is cosecant squared theta. So we'll keep our running list of the Pythagorean identities over here. And coming back to sine squared theta plus cosine squared theta equals 1. Instead of dividing by sine this time, we'll divide all three terms by cosine squared theta. And what we get here, if sine squared theta over cosine squared theta is tangent theta, and then cosine squared theta divided by cosine squared theta, well, that's just 1. And 1 over cosine is secant squared theta. 1 plus tangent squared theta equals secant squared theta. One last identity for the Pythagorean identities would be if we are starting with sine squared theta plus cosine squared theta equals 1. If I subtract cosine squared theta from both sides, I would get sine squared theta equals 1 minus cosine squared theta. And additionally, if I subtracted sine squared theta from both sides, I would get cosine squared theta equals 1 minus sine squared theta. And these two are actually pretty common. The next category for trig identities are odd and even functions. An odd function is one where f of minus x equals negative f of x. And what that looks like is if I have sine theta, and if I change that to minus theta, then that would be equal to negative sine theta. And originally, sine was positive here and became negative here. And this is a characteristic of an odd function. Now, symmetric with respect to the origin, and y equals sine of x is symmetric with respect to the origin, actually passing through the origin right here and swinging back and forth between +1 and -1. The other three odd functions would be tangent, cosecant, and cotangent. Here we can see tangent theta passes again through the origin. Here we have cosecant, and cosecant is symmetrical with respect to the origin again. And finally, cotangent is symmetrical about the origin also. Now, even functions are functions that are defined by having f of minus x is still going to give the same function f of x. And these will be symmetric with respect to the y-axis. Let's look at an example with cosine theta. And here we see cosine starts off as positive, and when we have a negative angle, we go to it still being cosine theta. Let's look at this on a graph. Here we have cosine theta, and we notice that it doesn't pass through the origin, but in looking at each side here, it is symmetrical with respect to the y-axis, doing the same thing on each side of the y-axis, but not necessarily at the origin. And the only other even function is, so secant of minus theta starts off as positive and still is positive on the other side, even when the measure of the angle inside goes negative. Let's look at the graph of that. And here in Desmos, we see that it's not symmetrical with respect to the origin, but rather symmetrical with respect to the y-axis. Moving on to cofunction identities. These are trig identities that show a relationship between trig ratios pairwise. It's easiest to understand it if you just see it. So we'll start off with cosine. And for cosine theta, that's going to equal sine 90 minus theta. And basically what all this means is that the graph is shifted 90 degrees out of phase. Just in case radian measure comes up, pi is equal to 180 degrees, and therefore pi over 2 is 90 degrees. Now, the simplest way to understand this would be to look at a single graph that has cosine and sine on the same graph to see the phase shift. So here we have y equals sine x, and we'll notice at 0, the function is equal to 0. And then 90 degrees out, it's going to be at +1 at pi over 2. So here now in black, what I have is cosine theta. And you'll see that where sine is 0, cosine is 1 at this point, and this is shifted exactly 90 degrees out of phase. And it keeps following the same pattern over and over. And if you just take the sine value and you subtract 90 degrees, you have the cosine value. And here we see that sine is cosine as 90 minus theta, and cosine is sine 90 minus theta. Going back to the graph, if I take the cosine and I subtract the 90 degrees, I get the sine value. 0 occurs at pi over 2, and here 0 occurs at 0 on the sine graph. Next one up, we have cotangent theta equals tangent of 90 minus theta. Here we have the graph of cotangent x, and now I've added tangent x in black, and we notice that at pi over 2, cotangent is at 0, and over here, tangent is at 0, 90 degrees before it. Let's take a look at how this is used. So if I have cosine 20 degrees, I would be able to use this relationship. So sine would be 90 minus theta from cosine, which is 20. So 90 minus 20 is 70. So sine would be 70 degrees. And that's pretty helpful because if I know one, then I would know the other. One way to know if you've got it right is that these two will always add up to 90 degrees. So let's try if I have sine of 40 degrees. Well, the cosine would then be 90 minus 40, or 50 degrees. And again, these would add up to 90 degrees. And if I had cotangent of 20 degrees, that would be equal to tangent of 70 degrees. And in alignment with the graph we just looked at, if I had cotangent of pi over 2, which is 90 degrees, I would have tangent would be the pi over 2 minus pi over 2, which would be 0. And again, these two would add up to 90 degrees. Double angle identities fall into a family of 3, so their sine of 2 theta is equal to 2 sine theta cosine theta. And then cosine has a couple of variations of it. So cosine of 2 theta, there are 3. So you have cosine squared theta minus sine squared theta. Another one that it can equal is 2 cosine squared theta minus 1. And the third one is 1 minus 2 sine squared theta. Now, these are just algebraic manipulations off of the same one. I'm not going to go into that at this time. Just be aware of them. My recommendation is if you're trying to have these available to you while you're doing practice in classes, to make up index cards for double angle, and then one after this will be half angle. Just make index cards up with those. And the next one that you're going to want to know is for tangent of 2 theta is equal to 2 tan theta over 1 minus tangent squared theta. And as you use these, they'll become familiar to you, at least when you're doing your work, practice problems. Little bell will go off in your memory that will say, I've seen that before. And writing them on index cards is one way to help you memorize them. Next, we have the half angle identities, and we'll start with sine of theta divided by 2 is equal to plus or minus the square root of 1 minus cosine theta over 2. Then cosine theta over 2 is equal to plus or minus square root of 1 plus cosine theta over 2. And the only thing that differs for these two is the plus and the minus sign. So easy to remember. The next one up is tangent for theta over 2. And remember that tangent is sine over cosine. So if I was writing these two and I'm dividing the sine by the cosine, I would do the copy dot flip of the fractions, and what I would get is the square root of 1 minus cosine theta over 1 plus cosine theta, because if I had sine divided by cosine for the half angle formulas, I would have this fraction divided by this fraction. I would do copy dot flip. These would simplify, and what I would have is this for the numerator and this for the denominator under the radical. Two additional forms for the half angle formula for tangent are done by doing an algebra manipulation to this. I'll do it for one of them just so that you can see how it's done. So here what I'm doing is I'm multiplying, I'm not changing the value by multiplying by 1, and 1 minus cosine theta over 1 minus cosine theta is still 1. But when I multiply these, an interesting cancellation will occur. So for the numerators, 1 minus cosine theta times 1 minus cosine theta is 1 minus cosine theta squared. And on the bottom, I would actually have to do FOIL. So multiplying the first terms, I get 1. Then the outer, then inner terms are minus cosine theta and plus cosine theta. And then the last terms minus, signs are different, cosine squared theta. Minus cosine theta plus cosine theta add up to 0, so we get 1 minus cosine squared theta. And if you remember from the earlier Pythagorean identity, 1 minus cosine squared theta equals sine squared theta. So I've entered that over here. Now, since this is taking the square root of two squared terms, I'm just going to get 1 minus cosine theta over sine theta, which is this form. And the same thing would work for this one over here. To get this form here, instead of multiplying by 1 minus cosine theta over 1 minus cosine theta, I would do plus and plus, and it would yield this one. This section of the video will be used to show you how to graph trig functions on a TI84 calculator. It'll also talk about how to zoom in and zoom out on a graph and to set the boundaries for the X and Y axis. Well, first thing I want to do is I want to go into mode, and when I'm working with trig functions, I have to select if I want this on radians or degrees, and it's really, we're not calculating anything right now. I'm going to set it to radians, and I've pushed enter. Now I want to push second, and the mode button is also, second function is to quit, so I want to quit there. Next I want to do is enter an equation, so I push y equals, and we'll start with something simple. So we'll push sine of x, so I push sine x, I'm closing parentheses here, and now I just push graph. And it's given me a graph, but one of the problems with this is it's really zoomed out. So there's a couple of ways. Obviously there's a button here that says zoom, and if I scroll down to where it says zoom in and I push enter again, it's zooming in too much for my purposes here. So I'm going to go zoom. I'm going to come down to 3, which is zoom out, and I'll zoom back out. And what I want to do to zoom in more accurately is I want to change the scale of the X and Y axis. So in order to do that, I push window, and then we'll see X min and max here and Y min and max here. And I want to set these so the boundaries, so for X min, we'll make that -3. We'll make it -2. And then I will come down to X max, and I'll leave that at 8. So now I'm going to come down, since my sine of X graph is only going to go from +1 to -1, we'll change this scale so it's -2 and +2. So my Y max will be 2, and then I push graph, and you can see it's greatly zoomed in. Now what I want to do is, let's say that I wanted to practice doing a transformation, and in this case I want to shift up 1. I would go back to y equals, go to the end, and simply push +1. And then I push graph again, and I notice that my graph has moved up 1 space on the y-axis. And I can see my frequency is set to just sine of x. But let's say I want to increase the frequency. So what I'll do is I'll go back to y equals sine of x. I'm going to come in here where it has the x, and I'm just going to put 3x. I'm increasing them 3 times the frequency. close parentheses, and we'll just take the 1 out. So it's not going to be shifted up, but I'm increasing the frequency. So now I push graph again, and we see that the frequency has increased by 300%. Let's say that you wanted to graph, instead of sine, I wanted to do cosecant. Well, cosecant is 1 over sine. So I would go back to my y equals button. I would push clear. And now what I'm going to do is I need to have, instead of sine, I'm going to do 1 over sine. So I put 1 divided by sine of x, close parentheses, and 1 over sine is cosecant. So when I push graph, it is now graphing the cosecant. But now, because of the change in the scale, I want to change that to zoom out so that I can see a little bit more of the graph. So I click Window, and I'm going to change my x min to -6, and we'll leave x max at 8. And now for the y, to change the height of the allowable values, I come down to y min, and I'm going to make that -6. And I'm going to come down and change y max to 6 also. I'm going to push graph, and you can see we just have, we've zoomed out a little bit so you can see a little bit more of the graph. So now I'm going to go back to y equals. I'm going to clear that. And this time I'm going to do cotangent. So to do cotangent, that's 1 over tangent. So I do 1 divided by tangent. I'm going to do x, close parentheses, and graph. And now I have cotangent. Let's say that I wanted cotangent and tangent on the screen at the same time. I would go to y equals, and I would come down to y2 for a second equation. And here I would put tangent x, close parentheses, and then push graph. Now it's showing both of them, and if you have the color version of the TI84, this is a plus CE, so it's in color, you would have both on the same graph and in different colors so that you can contrast them. If you would like a video made on any topic, or even one that shows how to use the TI84 in another application, comment below and I'll make the video for you.